All right, so we're going to sketch a graph now of a possible graph of f given the slope values here. And we're going to be given a starting value here just for reference, kind of a benchmark point, the origin 0, 0. Okay, so coming up here, the first thing I'm going to do is pick a flavor. I'm going to graph it on the same coordinate plane. What goes good with blue? Green. Okay, let's use green. I'll use a banana. All right, so f of 0 equals 0, so there's the first point. Now, what I'm going to do is follow the instructions of f prime, which again gives me the slopes, increasing, decreasing, and how I'm going uphill or downhill with the concavity. And as I go from one point to another, every time it changes its slope or its curvature, I'm going to connect it with a piece of the graph that resembles one of those four arcs of the circle, as we saw. If we know the sign of the first and second derivative, we know what the shape is. So from 0 to 1, since we have negative f prime values, our function is going what? Uphill or downhill? It's going downhill. How is it going downhill? Well, the slopes of f prime are the concavities. So since the slopes from 0 to 1 are positive, f is concave up. So I got to be decreasing, concave up. So decreasing, concave up, something like that. And I have to kind of go to a horizontal tangent line because at 1, there is a 0 value of the derivative, so horizontal. Now from 1 to 2, positive y values mean increasing. In fact, from 1 to 6, all my y values are positive, right? Bless you. So from 1 to 6, I'm going to draw it going uphill. And all I need to do is figure out how I'm going uphill by looking at the slopes. The slopes will tell me if it's concave up or down. Positive slope means concave up. So increasing concave up to about 2. From 2 to 3, I have negative slopes, so that's concave down, right? From 3 to 4, increasing, so positive slopes, so concave up again to about 4. And then from 4 to 6, it's going to be concave down because it's decreasing. Now, because it goes to a 0 slope at 6, I want to make sure as I approach 6, I'm approaching a horizontal tangent line, something like that. Now, from 6 to 8, my y values are negative, so f is decreasing. But from 6 to 7, negative slopes mean concave down. Then from 7 to 8, decreasing, concave up, because positive slopes. And then I hit a horizontal tangent right at 8, because it's a 0. Then from 8 to 9, increasing, concave up. Something like that. Now, the height at which I went, the y values aren't perfect, right? The only y that I know for sure is perfect is 0, 0, the one I was given. Everything after that is just kind of an approximation. And so you're not going to be judged too critically about that. But do notice something. If you're thinking about the x values as being time, you could say that, let's say like from 0 to 1, for 1 second we were going downhill. Versus from 1 to 6, for a 5-second interval, we were going uphill. So we're going uphill longer than we're going downhill. Also, the distance away from the x-axis you could think of as the speed, right? So we're going uphill, notice here at 5, at a maximum speed of what appears to be about 3. But we're only going downhill over here between 6 and 8 at a maximum speed of about maybe -1 or -1.5. So you want to think about that. For how long are you going uphill? For how long are you going downhill? And how fast are you going uphill and downhill? Simply because you might be asked to do this. Can you determine the x values at which the function you just drew attains its max or min? And by max and min, we mean what? Absolute, global, local, relative? Well, if we don't say which type, remember it's implied to be absolute or global. Is it possible to determine the absolute maximum where it occurs? On the green graph, the absolute maximum of f. This appears to be the highest point I drew, but is it possible that the right endpoint could have gotten a little bit higher? Yeah. Without any real quantitative analysis, I'm not quite sure where the maximum would be. So we can't really determine that. So you wouldn't be asked that necessarily. What about an absolute min? Is it definitive where the absolute min occurs? I think that one's a surer bet. I think we would agree that it occurs at x equals 1, because this is the lowest spot. Now the only other possibility where it could have been is at 8, right? But I don't think the way that it was going uphill and for the length of time it was going uphill, that coming back downhill from 6 to 8 was enough to bring it below where it was at 1. Would you agree? Yeah, because again, we're going uphill from 1 to 6 at a rate that got up to 3 miles per hour, if you want to say that. So coming downhill from 6 to 8 for only a 2-second interval at a maximum rate of maybe 1.5 miles per hour, it's not enough to bring it all the way back down below where it was at 1. So that's a definitive claim. So we could just say that F has a min at x equals 1. Is it possible to determine what the actual minimum value is? No, we can't. Not without any quantitative analysis. All right, so 2 skills there. Sketching a graph of F from F prime, and then trying to answer questions about absolute extrema. Now, of course, if you look at your graph, it should coincide with everything you answered about it, right? So if you ever see that and you feel like graphing it first might help you answer the rest of the questions, you don't have to do these in any particular order, right? A, B, C, D, you could do them in any order you want. All right, let's try example 8. Example 8, very similar except kind of different, but similar. The graph of the derivative f prime of some continuous function. So again, f is continuous everywhere. We're still on the interval from 0 to 9. It's shown below. Part A, on what intervals is f increasing? Is this the graph of f? No, this is the graph of f prime. Right, so we can't look to see where that graph is increasing. We're going to look to see where this graph is what? Greater than 0. So greater than 0 means above the x-axis. So it's here to there, there to there, and there to there. So 0 to 2, 4 to 6, and 8 to 9. On the open intervals, f is increasing on the open interval from 0 to 2, union 4 to 6, union 8 to 9. Justification, since what? F prime is greater than 0 on these intervals. On these intervals. And not somewhere else. All right. Any questions on that? That was kind of like the previous example. Part B. At what value or values of x does f have a local max or local min? Well, once again, a function f will have a local max or local min at either 2 places, where f prime equals 0 or where f prime equals d and e. We have the graph of f prime, so let's go look for its x-intercepts and any places where it might not be defined, knowing in advance that the function f is continuous everywhere. So any value where the derivative may not exist is going to be in the domain of the function. All right, where is this graph equal to 0? 2, 4, and 8. All right, so let me get those down. That's at x equals 2, 4, and 8. Those are CVs, possible local extrema. And is it ever undefined? At 6, right? There is no point at 6. But we know the function is defined there. If a student were to overlook one of those types, which type do you think he would overlook? The 6, the D and E, right. So now these are the candidates for local extrema. We need to determine if they're actual local extrema. And to do that, we need a sign change in f prime. Yes? We need a sign change in f prime. Bless you. So at 2, f prime goes from positive to negative. So that should be a local what? The location of a local max. At 4, f prime changes from negative to positive, so 4 is the location of a local min. Let's look at the other one over here at 8. F prime changes from negative to positive, so f would have a local min at x equals 8. Are you okay with the sentences on all those? You could clump 4 and 8 together, couldn't you? Because they change for the same reason. Now, let's look at the other one. F prime is not defined at 6, but f is, so it's a critical value. F prime is positive to the left, and f prime is negative to the right. Is that going to be a local extrema? Yes, which type? A local max. Right, it's a local max. And because it's a local max, but the derivative is undefined there, it's probably going to be some type of what? Cusp, right? It's going to be some type of cusp. All right, so you could group that one together now, believe it or not, with the one at 2. So I'm going to go ahead and just say the sentence. If you want to write it, feel free. F has local maximums at x equals 2 and x equals 6, comma. Since F prime changes from positive to negative at these points. Or you just state the points again. Also as well, additionally to, F has local mins at x equals 4 and x equals 8 because F prime changes from negative to positive at these 2 points. So by now, hopefully, that recipe for successful sentence writing, you have it down pat. You don't need to consult the cookbook anymore. Okay? Any questions on that one?
If one of the holes is like filled in, would it be like not being like?
Right. If that's a good question. Let's say this was filled in. Would it still be a critical value? Well, let's see. Critical values are, it would be in the domain of the function f, so we got that. We just need the derivative to either be 0 or undefined. Is the derivative equal to 0 here? No. Is the derivative undefined here? No. The derivative is actually defined to be about 3, so it would not be a critical value. But it would be a PIV at this point, right? Because the derivative of this graph, which would be f double prime, is now not going to exist. So it could be a possible inflection value, but it would no longer be a critical value. That's kind of interesting. I'm glad you brought that up. Okay. On what intervals is f concave down? F is concave down when the slopes of f are what? Prime. Sorry, slopes of f prime are negative, right? We're relating that directly to the graph. That's when f double prime would be negative. So it's where this graph is decreasing. Again, I don't want you to say decreasing. We'll just look at the slopes. But it is where the graph is decreasing. So there, all the way to there, the whole thing, right? And that looks like about it, huh? So f is concave down. We'll spell it out on Cinco de Mayo. CC down on the interval from 0 to 3. Since, and who wants to take the justification? Since that's where the graph is concave down? You could say since f prime of x is decreasing on that interval. That would not be wrong. But again, to stay in the habit of doing sign changes, since the slopes of f prime are negative on this interval. But either one would work. Since f prime is decreasing on this interval, or since the slopes of f prime are negative on this interval. Either one. Since the slopes of f prime are less than 0? Yeah, you could do that. Sure. Yeah, you could do that. Okay, state the inflection values of f. Well, once again, it's going to be where f double prime equals 0 and or f double prime equals dne. And that's going to be where the slopes are 0 or the slopes are undefined. The slopes are going to equal 0 at the critical values of f prime. That was kind of like we did in the warm-up. So at 3, that's the only place where the derivative is 0. The slopes of this graph are 0. Are the slopes of this graph ever undefined? Yes, where? At 6. If the first derivative is undefined, the second derivative will be. So 3 and 6 are the only candidates. So we get x equals 3 and x equals 6. Now we're not going to stop there. I know that relates it directly to f prime and not the slopes of the graph, but we're going to handle that in our justification. We want a sign change now in the second derivative, which means we want the slopes to change from positive to negative or negative to positive. At 3, bless you, our slopes change from negative to positive. So is that an inflection value? Yeah. And at 6, our slopes change from positive to positive. Oh, they don't change. Oh. So is 6 an inflection value? No. So only 3 is. Okay, so the sentence would be f has an inflection value at x equals 3 since the signs, or the sign of f of the slope, the sign of the slope of f prime change from negative to positive at x equals 3 also. That's where it happens. Yep. Sign change in the slopes. So it is an inflection value. And then the last part here, very similar to what we did above. Assuming that f of 0 equals 0, sketch a possible graph of f. And if you can, if it's possible, determine the x values only where the absolute max and min occur on that closed interval. I'm going to let you give that a try, and then we'll kind of see how you did. Because this one's kind of interesting. You know how it's supposed to be done now? You can use the information from the previous example to help yourself. What's happening at 6? That's a good question. Did it crack the screen, or just
It looks like it's just a little chip.
there's a blemish on the screen?
Yeah.
You play with it? Yeah? Looks like someone sneezed or something. Big sneeze. Did you laminate your flat Stanley thingy?
Yeah, no.
Yeah.
Miss Ortiz.
Oh, she laminated everybody's.
Yeah.
Oh.
Because we have to take pictures of them with them for the rest of the year.
For the rest of the year?
Yeah. So she's like, we don't want them falling apart.
And what's the purpose of taking a picture with him the rest of the year? The Lorax, right? Yeah.
She'll give us like a little topic kind of thing. The 6 weeks is either you can take a picture, you have to take 2 pictures of either one or the other. And it's water conservation and no animal cruelty.
Oh.
You take 2 pictures of one or the other, or a picture of each. You just take a picture.
So you have to, it forces you to put yourself into a situation where you're aware of those ideas. And he's just an excuse to
basically
document that you're considering it.
Yeah.
I should do that with a little Einstein. Yeah. Or
Einstein followed her from the museum.
from the Night Museum?
Yes, the Night Museum, the movie.
I've only seen the first one. Yeah.
Second one, like Einstein.
Oh, bobblehead. Yeah. Ooh, yeah, nice. I see some sharp things. It's helpful to sketch it on top of the original graph. It's not required, but that way you don't have to kind of redraw the scale, and you can kind of refer to it pretty quickly. What's that? Oh, screenshot and then insert. Oh, there you go, so that you don't. That's nice. Good idea. That's using technology. Give me about 2 more minutes, and then we'll see how you did. Once you have the graph, can you figure out the x-coordinate of the absolute max and or the absolute min? You have 2 cusps on your graph. Are we supposed to have 2 cusps? The derivative would be undefined at both of those. And notice our derivative is only undefined at 6. Here's what you could do. Once you think you have a prospective graph of f, you could actually try to think about taking its derivative and graphing it, and you should end up with this. Because we've done that before on a warm-up. Everywhere your graph that you generate has a horizontal tangent, it needs to be an x-intercept of f. Wherever your graph is going uphill, you should have positive y values of this graph, so on and so forth. Kind of understanding it both ways. All right, does anyone think they have it? Anyone want to volunteer your graph? All you have to do is log on and you can be on the video. Who's got it? Come on, somebody. I've seen several correct ones out there. Anyone? Jackson, let's do yours. Because yours is in the front row. Oh, you've locked the screenshot? AirPlay. I don't know. Ready for Jackson's? Here comes Jackson's. Yeah, I see his right here. Did anyone else get something similar to that? Yeah? Okay, let's see if it's right. We're increasing from 0 to 2, so his is going uphill. Because f prime is a negative slope, we're going to be concave down. And he approaches a horizontal tangent at 2. Perfect, okay? Then from 2 to 4, since f prime is negative, our green graph is going to be going downhill. From 2 to 3, though, the slope is negative, so it's still concave down. And then right there around 3, he has an inflection value. The local max and the local mins of our function f prime are going to be the inflection values of f. And then it's increasing, so it's concave up as it goes downhill. And then he has a horizontal tangent again at 4. From 4 to 5, positive y values, positive slopes means increasing concave up. Now, he has a cusp right here, which is great. Your cusp could be, I don't think the slope is approaching infinity. If you notice what the blue graph is doing, the slope as you approach 6 is approaching what looks like to be 3. So if you have like a slope of 3 on one side and maybe a slope of 3 on the other, negative or positive 2, sorry, it doesn't always have to be like a vertical cusp. It could be something, like his. It doesn't quite go vertical. But then it's increasing again on the other side, so it's still concave up on the other side. So you can see that concave up on both sides is not an inflection value, but because f prime changed from positive to negative, it's still a local max. Kind of looks like the Matterhorn Peak for those of y'all who were there this past summer, right at the Matterhorn Peak. Emily, y'all were there, right outside the Matterhorn. Did it look like that? Yeah, maybe. Jackson, can you draw like a little snow cap on there and make it look more like the... There you go. There, now it looks like Matterhorn Peak. Matterhorn Peak is iconically one of the pointiest peaks. The Eiger is pretty pointy too. Okay, so then we've got positive y values from 8 to 9 and positive slopes, so then it's going to be increasing concave up. So perfect. That could be the graph. The positioning of the y values could fluctuate a little bit. Now, just looking at that, is it possible to determine the x location of the absolute min? Maybe. His min is at the starting point, right? Did anyone draw their graph that it dipped below the x-axis when you came back down either time? Is it possible, plausible, that when we turned the corner, we could have actually gotten back down to the x-axis or maybe even dipped below it? Baloney. I don't think it's as definitive that we stayed above the x-axis, but I wouldn't argue if you said we did as well, because notice we're going like uphill from 0 to 2, and we're going downhill from 2 to 4. So it's about the same amount of time, right? 2 seconds. But notice we're going uphill at a rate like 3 miles per hour, and the lowest value here at 3 is only negative 1 miles per hour. So I think we were going up faster than we were going down, so I don't think it dips below here at 4. And then we're going up from 4 to 6 at a rate then that was approaching 3, and we're going downhill from 6 to 8, which is about the same amount of time, and we're only going downhill at a rate that approaches 2 instead of 3. So again, I don't think we're going to make it back down to the x-axis again. So you could argue then that yes, the absolute minimum could occur at the left endpoint at x equals 0. I would go for that. Does that make sense? Why? Now, what about the absolute maximum? Is that going to be as definitive? I don't think I can make a rational case for that, because maybe it's here at 2, maybe it's here at 6, maybe it's even at the right endpoint. There's 3 candidates, and without any real quantifiable data, I don't think we can really make that claim. All right. Awesome. Very good. Any questions? All right. You can go ahead and take yours off then. And by the way, there's no password on my projector, so if you want to scroll up and go to AirPlay, let's see what it would look like if we all project at once. Let me do something first before y'all do that. If you're asked to do that, like on a video, or not on a video, on a question, like a free response, it might say, here's the graph of f prime, and the graph might be doing something like this, and then it'll cross right here, let's say at x equals 5, and it'll go downhill till 6. So if this is the graph of f prime, is it possible to determine where f attains its absolute minimum? If this is f prime, is it possible to determine the x value where we attain the absolute minimum? Well, yes. Notice f prime is going uphill from x equals 0 to x equals 5 right here, right? That's where that graph is positive. Now, assuming we start at 0, 0, we don't have to assume that. Let's just go uphill, essentially, till 5. And then it goes downhill from 5 to 6. Yeah. Where's the absolute maximum? I'm sorry, absolute minimum? I asked that first, didn't I? At 0. Is it also, can you determine where the absolute maximum occurs? Yeah, at 5. So in some cases, you can determine both of them. But if there's any kind of ambiguity like the previous one, it's not going to happen. Okay, go ahead and project this there. Let's see what it looks like. I've never done this. I'm curious how many little squares we can get up there. Scroll up from the bottom, go to AirPlay. It's the one that has like Corpy with like 5 zeros in front of it. And just turn your mirroring on. Oh, there's one. Okay. Ooh, yeah. Oh, yeah. Look at that. Oh, water. Jaws. Shark. Okay. Oh, yeah. Nice. I don't know what the limit is. Oh, look, we got a dancing sombrero. Señor Salsa. Somebody's not been paying attention. Unless you can draw really fast. That's awesome. Oh, okay, that's Waldman. Is that it? Has everyone tried? Is that the limit right there? Some of y'all haven't tried. Oh, sublime. Interesting. Oh, that's kind of creepy. Hello, world. All kinds of great messages. Hey, well, we're done with the notes, so the worksheet's due tomorrow. The folder's already in e-backpack, and we'll quiz tomorrow as well. Sound good? Now, during next period, I do ask that you don't kind of intercept and project to my computer from the other side of the school. Okay. Have a great day. Bye-bye. Oh, thank you.